So I will continue with what I did last time. Namely, I will continue with the proof of Matsushita's theorem. I will talk a little bit more after that about fibers or bases of Lagrangian fibrations. So last time we had F from X to B, a fibration of an IHSM called X, and we have the assumption that the dimension of B is positive and strictly smaller than the dimension of X, which is 2n. And we discussed a couple of things. For example, we learned that a circle of implications is not the same thing as a circular argument. So the circle of implications is one, the circular argument is not. What else did we prove? I think we showed, so recall, you've seen that if B is projective or scalar, then necessarily the dimension of B is equal to n. Another thing we have seen is that, so assuming this, so B projective or scalar, then using the first step also implied that the general fiber F is Lagrangian. And I think that's where we will continue today. So let me, without drawing the diagram again, add another circle to it. So I think, it's clear that if I am, it's clear if you know what a singular scalar variety is, that if B is projective, then B is also scalar. I mean, projective means you can embed into some high-dimensional projective space. The only thing you need to know about this notion of scalar is that if something is scalar and you have a subvariety of it, then the subvariety will also be scalar. Projective space is scalar in the classical sense. Therefore, if this is projective, you can embed in projective space, then this will also be scalar. So for the converse, there is a novel theorem of Montesson, or the Montesson criterion. So if you have B that is smooth, if B is smooth, scalar and Montesson. So again, a Montesson manifold or a Montesson variety was a variety that was bimeromorphic to a projective variety. So in particular, all algebraic varieties by Chau's theorem are Montesson. So if B is smooth scalar Montesson, then B is projective.
Why B is compact?
Sorry?
Why is B compact?
Yeah, compact, yeah. Everything is compact. B is compact. Yeah. So you recall that there was this, in this big diagram, there was the statement that B as log terminal singularities. So we had an arrow from here to there, and B, I could have added another point saying B has rational singularities. So this implication is a classical result. If B has log terminal singularities, then it has rational singularities. And the good thing about rational singularities is that Moisesan's theorem generalizes to this class. So if B is compact and has rational singularities, then it's projective as soon as it is Moisesan. Kähler and Moisesan still will imply projective. So this allows us to go the other way if B is Kähler.
So you insist on this cycles.
Yeah, I love it. And so this cycle is independent of all the other cycles. So that tells you that from now on you can equate Kähler and projectivity. And I won't show that this arrow that Kähler implies log terminal singularities, because that's not fun, but in any case it's a true statement. So in the context of Matsushita's theorem, the base being projective and the base being Kähler are equivalent statements. Okay, so let's go to the next step. Actually, I think I shouldn't call them steps because I will not give the complete proof, and saying step suggests that at the end I will put all of them together. So it's just some part of the proof that I will show here. Namely, so assume the projective.
I'm sorry, step 3 of the proof of the Matsushita's theorem.
Of Matsushita, yeah.
Sorry, pretend to take a question.
So, this is an old theorem, meaning that nobody knows the proof anymore. So, step 3 of Matsushita. Assume that B is projective, and then we'll show that the general fiber is an abelian variety. So first, see that there is, as soon as give it a name, general fiber is called F. F is Lagrangian. What we've already discussed. And whenever you're in this situation that you have a vibration where the general fiber is Lagrangian, then on the general fiber you find an action of C to the N on F, which is transitive and well, okay, I mean, eventually it will be transitive, but what you show in the first place is that with everywhere n-dimensional orbit. So this is an action just by Hamiltonian vector field. So you take a coordinate system in the base, you look at the corresponding one forms, then you pull them back, so you get differential forms on X, at least locally, and then you send them via the symplectic form to the tangent sheet, so you get vector fields on X, and these vector fields they generate the flow associated with these vector fields into a Cn action that preserves the fibers. And the fact that these vector fields are everywhere linearly independent shows that you have an n-dimensional orbit everywhere. So this implies that Cn acting on F is transitive, and you can see that the stabilizer is a lattice, and therefore this has to be a complex lattice. That's a classical result from symplectic geometry, and so in particular that also applies in the real symplectic situation. The argument I would like to give now is, why is this complex torus projected? I want to prove that F is projective.
And for these, you don't need to be projected. No?
Sorry?
For these, that you don't need to be projected.
Well, I need B projective because until now I have not shown that the fiber is Lagrangian without the assumption of B. So to prove that F is projective, we consider B, which is the image of say H2 of XR to H2 of FR. There's the restriction of real degree 2 cohomology classes. I want to apply the Dirac theorem that we've already seen in Yada's lecture. So I want to find a rational Kähler class. Once you have a rational Kähler class, it comes from, or at least the multiple comes from an ample line bundle, and then of course you have to project it.
This is, sorry, V is the image of this map. Is that what I'm reading?
V is the image of
Okay,
this.
great. No offense to the German handwriting style. Sorry.
You're really unreadable?
No, it's good writing. I just I'm stuck in my American handwriting ways.
Okay. Okay, so V is this image, and how do you find a rational Kähler class inside of it? So first of all, note that so the image of this inside H2 FR is dense inside of me, right? Because it's dense in H2XR. And then, so I claim that the Kähler cone, so the image of the Kähler cone inside H2 FR is open. Yeah, so once I have established these two things, a dense set and an open set, then I'm good, right? Because then I find something in the intersection, by definition of what dense means. Okay, how do I see that this is open? For this, you just consider so H2X R, which can be decomposed as H20 plus H02. This is defined over the reals, plus H11. Okay. So it's R. Then the map to H2 FR, if I restrict it to those summons, well, here, this composition is 0. That should be 0 because F is Lagrangian. Right? So F is Lagrangian, that means H20 goes to 0. Conjugate also goes to 0. Therefore, this whole piece goes to 0. So the image, so V, so this actually surjects onto V. Right? And now you know that the Kähler cone is open inside here. You have a surjective map of vector spaces. The image still is open. All right. So this proves the second claim. And therefore, any alpha in how should I call it? In the intersection of these two spaces. So in the image of kappa to V intersected the image of H2XQ to be different from 0. Oh, sorry, Kähler class never goes to 0 is a Kähler class on F is a rational Kähler class on F. Then by Kodaira you conclude that F is
general.
Sorry?
For the general.
So for the general. I claimed it for every fiber. I won't prove anything. Okay. Let's prove something else of those things that I claimed. Let's prove that V is projective, then the Kerr number of B is 1 and B is finite. Okay. I will give an argument for this first claim and only sketch the second one. So, yeah, how does this work? If you have L and take B not torsion, then it was L, the C1 of F upper star of L. We have, I'm wondering what do I actually need? Well, I list a couple of properties. I don't know whether I need them all. So we have Q of L is equal to 0. L is different from 0. And Q of L and omega is positive, where omega is a Kähler class. And as you've seen yesterday, also this proof will be essentially some clever use of the, or in this case, even not that clever, use of the quadratic form. So, yeah, let me call that something lambda L, positive real number. So now if you have, now it's kind of a stupid argument. So suppose you have L and M in pick B, not torsion, and then you just look at so I think I'll look at something like lambda M times L plus lambda L times M, or probably minus, where M is C1 of F upper star of M, and L is C1 of F upper star of L. And lambda M and lambda L are the same numbers as on the other board. So I guess now if I take the pairing Q of this guy here with omega, then this should be 0, right? Yeah, essentially by definition. Okay, so now Q on H11 signature 1 comma row, no, sorry, H11 minus 1. So therefore Q restricted to omega perp is negative definite. So in particular, if you have something that's in omega perp, all right, yeah. So okay, this is what I was still missing. Q of lambda M times L minus lambda L times M is moreover 0 because these things come from downstairs, and everything that comes from downstairs vanishes if I look at the square. Right? This was due to Fujiki. Highest power is 0, and therefore the Q of it is 0. Okay, well, so this means that lambda M L is equal to lambda L M. So these classes are proportional. Become number 1.
How do you use that L is not torsion exactly? How do you use this?
I use this because I want this class to be non-zero. The line bundle L were torsion, and I can't guarantee that the pullback is the first chunk class is 0 in that one.
You don't want to stop intersection. So where is this QL omega positive coming from?
Actually, I just need I just need it to be different from 0, so that this equation is a non-trivial equation. I want M and L to be proportional. Therefore, I need the coefficient.
How do we know that for no big 0? Because if L is in big 0, then the third class of product is 0.
Oh yeah. These simply connected.
How do we know that?
This is what we know, and I will explain that later. Maybe I could have put it here just as an assumption to avoid.
So the question was, why is L in pick 0? What was the question?
The question is what L should be non-torsion, but in big 0, say infinite order.
How do you define if a rank? Is it rank of Jones Severi or the Picard group? Maybe
Yeah, it's rank of Nernst.
Then maybe we can work on
So I could take L in there is a variable portion. Is that okay? I think that's also important.
Okay.
Yeah, thanks. So what else? Oh yeah, I wanted to show that it is final. So if f from x to b, and so if x is projective, then there is an inequality like that. The Kodaira dimension of x is greater or equal to the Kodaira dimension of f, where f is the general fiber, plus the Kodaira dimension of b. So you see the Kodaira dimension of b is smaller or equal than 0. That's if x is projective. Same conclusion holds. So I should say that's a theorem of Kawamata, which I think is not known to hold in the analytic case. Same conclusion holds. So this conclusion holds for x scalar by, let me just say, by some Kähler-Einstein argument. I don't want to give here, just some of the message is by a general argument you get that the Kodaira dimension of the base is either minus infinity or 0. So has to exclude that kappa of b is equal to 0, but this would be a contradiction to I forgot actually. So I think the argument was something like if the Kodaira dimension is equal to 0, then you could after some finite cover, produce a holomorphic form of top degree on B, which is not the power of symplectic form. So that would be a contradiction to I don't know how to formulate it, and I don't remember the argument precisely, but I think
you really do that just become one. So it's true that up over the amount of units to the you are using to become one. The economy is one. So
yes.
the base can be the canonical of B can be ample, anti-ample, or real.
Yes, I excluded the canonical being ample. Now I have to exclude that the canonical is trivial. That's what I'm trying to argue. But, honestly, I don't remember, but it's some clever argument that would contradict the algebra of holomorphic forms being generated by the symplectic form. Let me see.
That's what you said, that the symplectic form will not come from the base.
Yeah.
And here.
Yeah. Yes, but I mean, somehow I need to argue that the holomorphic n form can't come from the base here.
So it depends on the polarity.
Yeah, okay. One case is trivial, the other case I don't remember.
Comes from the fact that the n power, n over 2 power of this symplectic form does not come from the base.
Oh yeah, of course. Thanks. Okay, great. So, yeah. Thanks. So okay, let me let me summarize what you were saying. So if you have this assumption, you after maybe some finite cover, you produce a holomorphic end form that comes from the base, but no holomorphic form comes from the base because the symplectic form doesn't come from the base. Okay, so then using rho of B is equal to 1, you see that KB, or minus KB has to be empty. Right, because it's not 0 and KB, so one of somebody has to be. Okay. Now we have a lot of properties. I think I would like to show the equidimensionality. Well, that is a nice argument. And then maybe say something about the situation where we don't assume the base to be primitive. Okay, so that would be step 5 or so. And as I said, it's silly to call them steps because. Okay, so. Yeah, so equidimensionality. Equidimensional, again, if B is projected. The equidimensionality goes as follows. You use Kolar Saito theorem saying that the higher direct images of the canonical sheaf are torsion free. And in particular, I mean, we're on a symplectic manifold, therefore the canonical sheaf is trivial. So this is R I F lower star of OX. Right, so you take H2 of X OX. You have a morphism to H0 of X R2 F lower star OX. And so how does that work? Well, if you have a homology class, I mean, what's this here? So on an open set, this is the sheaf that's associated to on an open set, you take the second homology of the pre-image of that open set. So you can just restrict to such open sets to get a morphism like this. So now you take C, a component of a fiber of F. And of course, from here, you can go further to H2 of C OC. And you can even go to the resolution of singularities. So C tilde, you see a resolution. You can go further to H2 of C tilde OC tilde. Now the point is that if you have sigma bar, so the class corresponding to the complex conjugate of the symplectic form here, don't seem to be having.
I'm thinking about H0 of X R2 F star of X. R2 F star of X is a sheaf on B.
That's a sheaf on B, yes. Oh.
And how do you get a map to H2 zero?
That's somehow by taking the fiber. Right? So I mean, if I take, well, suppose that C is a component of the fiber in some point T,
Okay.
then you can take the fiber of this sheaf at T. If these sheaves were compatible with a base change, then the fiber at T of R2 at lowest or OX would be the second homology of the fiber. It's not compatible with base change, but at least you have a morphism of this relation. Well, first you go to the fiber, and then you stick to the component. Okay. So now I take sigma bar inside here, and the point is, this goes to a torsion section in this sheet, because general fiber is Lagrange. Yeah, so therefore, for general fiber, you map to zero, but this is torsion free. So by Kolar and Saito, this has to be zero. Okay, so if you take the symplectic form, or rather its complex conjugate, you restrict to C or to a resolution of singularity, so that that's zero, and therefore, so that's one point, and now I will prove that it's actually non-zero if the dimension of C is strictly greater than n. Then sigma restricted to C, and you can take the regular part of C, is non-zero by dimension reasons. Right? I mean, if you have a symplectic vector space of dimension 2n, you have a subspace that has dimension strictly bigger than n, the form cannot restrict to zero, just by linear algebra. So I'm doing the same thing here. We take a smooth point of C, restrict the symplectic form, and it cannot be zero if the dimension of C is strictly greater. This, of course, then also holds for the complex conjugate, but that's a contradiction to what we just had. So by the left board, we have that the dimension of C is smaller or equal to n, and then you use upper semi-continuity of the fiber dimension that says if you have a family where the generic fiber has dimension something, and the special, I mean, the dimension can only go up on the special fiber. So the semi-continuity of the fiber dimension means that the dimension of C is greater or equal to n, so therefore it's equal to n.
Have like a line sticking out of the plane, something like this. Sorry, component of smaller dimension sticking out of component of big dimension, like general maybe like n dimension, but like something sticking out of this. Reducible, consisting of several components, smaller dimension. C going to be like a line sticking of a half-dimensional fiber.
Oh, actually the semi-continuity of the fiber dimension is local, so you can do that around every point. Okay, this proves equidimensionality, and on the way also the fact that the fibers are Lagrange. Equidimensional and fiber components are Lagrange. Okay? Yes, well, in the end, step 7, up to 5, number 6. The Montesson, let me only sketch that because I want to say something about the fibers. So the Montesson, so what you show is up to bimeromorphic modification. B can be assumed Kähler and smooth. So why Kähler? That's a theorem of Fujiki saying that the Duodee space of the Kähler space is Kähler, and you can identify, well, at least an open set in the base with the Duodee space of a general fiber of the vibration, and smooth, of course, because you take a resolution of singularities, and then show that the H20 of this B, the smooth one now, is equal to 0 by the same argument that we always use. Right? If you had a holomorphic form on the base, you could pull it back, but upstairs no form is pulled back from the base. Okay, therefore the H2 of BC is equal to the H11 of BC. Then we conclude with Kodaira. Right? I mean, this in particular holds for the real numbers then as well. And then you again find a rational Kähler class inside here to get an ample line. Okay. Great. So much for Matsushita's theorem. And now, yeah, what do we have? We have that the fibers are Lagrangian. Smooth fibers are abelian varieties. And the base is Fano and Picarin 1. And because we discussed that before, here's a small lemma saying that the base is actually simply connected. So pi 1 of p is 1. And not only p, but also pi 1 of the regular locus of p. So the base and the regular locus are simply connected. Can I just ask, how many of you have seen this statement before? Okay, great. And maybe it's worthwhile giving it because it's something it's a stupid trick, and you have to see it once. So if P1 of B were different from 1, then there exists a topological cover B tilde to B. I have my vibration here. I can just pull it back. And you know that X only has trivial couples. Well, X is simply connected. So therefore, you find a splitting here. And then this vibration factors over a non-trivial cover. It's not possible because the fibers are supposed to be connected. If here a point has several pre-images, then the fibers would be the pre-images of that, and I think that's what we would do that. All right, so this was in case that pi 1 of D is different from 1, so if pi1 of D rec is different from 1, then you do a pretty similar thing. So just write D rec everywhere, and here, so to speak, the pre-image of E-rec under F. But this also has is also simply connected. So pi1 of x minus f to the minus 1 of E sync is also 1 for codimension reasons. Right? You know that the singular locus has codimension at least 2, the map is equidimensional, therefore the pre-image has codimension at least 2. If you take away something of high codimension, then you don't change the point. Okay. So let's go and say something about the existence of singular fibers. So, fibers. Existence of singular fibers. So if f from x to b had no singular fibers, then the Ri f lower star of z x, these are local systems. We've seen that the base is simply connected. This would be the trivial local system. And therefore, isomorphic to, well, the I-cohomology of the Abelian variety. And the constant local system, sorry, on B corresponding to that, and this is something like lambda I of z to the 2n of B. Okay, and I think now you just look at the Lorentz spectral sequence. For Zx. And more precisely, whenever you have a spectral sequence, then there's a associated sequence, 5-term long set sequence. So that goes, in this case, from age 0, I think, of so I think that's H1 of f lower star of Zx to H1 of Zx, so upstairs, to H0 of R1 f lower star Zx to H2 f lower star Zx. Correct? And well, it's called 5-term because there is another term, but we don't care about this. So the f lower star of on ZX, that's just ZB. So you have connected fibers. So here you have the first cohomology of B, and here you have the second cohomology of B. You know that this is as rank equal to 1. On the other hand, here I just argued that this is what? This is Z to the 2n. So this group has rank equal to 1, and this group is the H0 Z to the 2n on a connected space. That's just Z to the 2n. And yeah, the H1 of integer cohomology upstairs, that's 0. And you see between something of rank 1 and something of rank 0, you will never be able to fit something of rank 2n. So that's the contradiction. So as in the case of K3 surfaces, you see that there are singular fibers. Now I will try to mimic everything I told you for K3 surfaces. For example, ask how the singular fibers look like. Well, there is something known in the higher dimensional case. So remember, in the case of K3 surfaces, Kodaira classified the possible singular fibers that could show up. And now there is a theorem of Wang Chorizo. Well, not classifying the all singular fibers, but at least the generic ones. So that F, that's capital F, be a general singular fiber of Lagrangian fibration F from X to B. Then, so there exists a Kodaira singular fiber F0. So F0, that means it's a singular fiber of an elliptic surface. So I mentioned F0 equal to 1. That's one of the things that show up in Kodaira's classification of singular fibers of elliptic surfaces. And an action of group C to the n-1 on F, such that F is the orbit of C n minus of F0 under Cn minus 1. Yes.
Sorry, I think I didn't understand the last sentence. Then there exists a Kodaira singular fiber of dimension 1.
Yeah, a Kodaira singular fiber is a singular fiber of an elliptic fibration of a surface. So
We didn't assume surface anywhere. I just missed the jump to surface.
well, I'm just saying this is a sub in F. There exists a sub in F, a sub variety in F.
That's not the whole fiber of this map, little f. It's just a part of it.
Just a part of it.
Okay.
And then there's a Cn minus 1 action that translates it.
Sorry, I think I'm feeling tired on this.
What you should think of is, you know how. So this, for example, is a Kodaira singular fiber of an elliptic surface, and now think that the fiber F, that's F0, F could be something like that. You have an abelian variety of dimension n-1, and you have something like that. Transversely, your fiber, the whole thing here, that is F, and transversely that looks like the Dirac singular fiber. And then here, well, in this case, you would have an action actually by this abelian variety, and this Cn-1, you have to think of it kind of as the covering, the universal cover of this abelian variety. Okay, so essentially what it tells you is that the general singular fibers of Lagrangian fibrations in higher dimension look transversally like the Kodaira singular fibers of elliptic surfaces. Thank you. All right.
Does that mean that locally have a slice which is looking like a 0 times Cn, or it could be worse than that? Does that mean locally we have a slice which is like the product of F0 times some line space?
I think locally that is true, yes.
That's true, okay. It's not like that one really contracts them.
No, but there's an interesting thing happening. So, because I mean, so here's an example. If you look at an elliptic K3, so K3 fibered over P1, and you look at the Hilbert 2 of S fibering over P2. So what's that? You have the Hilbert-Shaw map to the second symmetric product. You have the morphism to the second symmetric product of P1. This is P2. And now look at, say, you have a point P here over which you have a non-singular elliptic curve, a non-singular fiber that's an elliptic curve. And here I want to look at the point 2P. What I get at point 2P is, well, I have the second symmetric product of the elliptic curve times, so this is on the symmetric product, well, okay, I'm supposed to live in here. Then I take the projective space of Ts restricted to E. That's a projective bundle over E. Right? So these are my two things, my two fiber components of this singular fiber. And they intersect, so E2 intersect PTS restricted to E. That is just the elliptic curve. That's just an elliptic curve E. So this elliptic curve is a section here, and it is only a 4 section here. Right? So when you have two irreducible components, but then how you get this F0? So this F0 is you take, I think what you do is you take a fiber of, so inside E2 mapping to E, so that's a P1 fibration. So inside here you take a fiber, and this fiber meets this 4 section at 4 points. At this 4 points, you view in the fibers of the other fiber. So these fibers, so this lives in E2 times E of PS. You have these 4 components live inside here. Maybe I could do that with some color code. So these 4 components live inside here. And this component is inside here. And if you look close enough, then this comes with multiplicity 2, whereas the other 4 come with multiplicity 1. And so then this is the Kodaira singular fiber at 0. So you have 5 irreducible components there, but only 2 irreducible components there. That's because some of this action of Cn minus 1, of C1 here, that moves these curves into one another at some point. So actually, if you think in terms of graphs, so if this is the graph of the Kodaira singular fiber, and the graph, some of the combinatorics of the components of the singular fiber F, they're just a quotient of this graph by the automorphism that is rotation. If I divide out by this automorphism of the graph, then I get 2 components corresponding to the 2 components of F, whereas I only have I have 5 components on F0. Be careful. Yeah, maybe I'm over.
In the figure of 1 with the ratio, X0 may not be a Kodaira fiber, so maybe anything start of 1.
Yeah.
Do you know if this can be realized or?
Yeah. That can. So that can easily be realized. You just take the thing I have here, and you fold it, and you glue along a non-orthogonal section of the elliptic curve. And you take some of a fiber, and then you take the next fiber at the point where you glue this. You have. So you take this, say, P1 bundle over a Abelian variety of dimension 1 less, and you have 2 sections along which you glue, but with a shift. Okay? So a shift like that, and you glue this curve with this curve, and so on. If that's a non-torsion gluing parameter, then you get an infinite cycle of rational curves.
But it actually not using that value.
What do you mean?
This is the distraction of the fiber, but doesn't actually.
Yeah. That's not difficult to realize. Yeah, I must say I write that under the rug. So F0 can indeed be a little more general than Kodaira singular fiber. But I think that's the only.
Exactly.
That's the only.
In the paper they had also D3, but then
I rolled it out later.
They ruled it out.
Okay, that's the question.